what we're going to do now is we're going to build upon the discussions we had last time with our accidental complexities. Did anybody remember what was an example of an accidental complexity? Or what is an accidental complexity? What's the definition of an accidental complexity? Makes a good quiz question, by the way.
It's not intrinsic to the problem?
One that's not intrinsic. It's typically a self-inflicted wound, right? You're shooting yourself in the foot because you're using libraries and languages and toolkits that are very low level, or you're not using your debugging tools properly. You're not using the debugging tools that you have at your disposal. You're using primitive debugging tools. And one way to solve a lot of these problems is just to use newer stuff, right? Use newer languages, newer platforms, newer tools, and so on. There's also these things called inherent complexities. And these are really the fundamental challenges in a domain. And of course, if we were talking about databases, there'd be one set of things. If we were talking about distributed systems, there'd be one set of challenges. We're talking about concurrency here, so we're going to be talking about inherent complexities of concurrent mobile device software. So in some sense, it's the rocket science, right? It's the really hard stuff. Just using a better language, just using newer tools won't make some of these problems go away. They sometimes will help, by the way, but they don't make the problems just disappear. So one of the things we're going to talk about is synchronization. We'll talk about that in a second. We're going to look at a couple different dimensions of synchronization. Then we're going to talk about deadlock, and we're going to talk about performance. Those are the key inherent complexities we're going to cover. There are other inherent complexities as well, things like starvation, which is another sort of, it's the inverse of deadlock in some sense. And we'll talk a little bit about that. As we do this, I'm going to show you a bunch of examples to make the point a lot more clear. I don't know about you, but I always feel better if I see working code, right? Just talking conceptually is a little bit too abstract. So we're going to show some code examples to illustrate what goes wrong when you don't use synchronization properly. And the things we're going to talk about are data corruption due to these things called race conditions, and also then having threads execute in the wrong order. They fail to coordinate their activity properly. So we're going to look at a couple of different examples. All of these examples are things you can actually download and play around with to get a better sense of it. And then later, as we get through discussions of some of the things like Java monitor objects and semaphores and condition objects, etc., you'll get a chance to see how to fix these problems, and you'll get a chance to program them. So let's start by talking about the inherent complexity of synchronization. There's lots of different ways to think about synchronization. I like to think about it as a way to ensure that interactions between computations occur in the right order, at the right time, and don't accidentally corrupt shared data. So you'll see that there's more to it than that, but that's the basic idea, and you can read about it here at the Wikipedia article. There are two key parts to synchronization. One part is ensuring mutual exclusion, which is kind of what we were just talking about here. We want to be able to make sure that during a critical section, a place where atomicity is important, that only one thing at a time is executing in that part of the code. So that's basically the issue of mutual exclusion. And we gave the funny example of the restroom where sort of FIFO ordering and one in, one out, fully bracketed. The person that goes in should be the person that comes out, and so on. So that's an example of mutual exclusion. The reason why you want mutual exclusion is to avoid race conditions. And as we had just talked about, race conditions are these scheduling hazards or these concurrency hazards that arise when the correct behavior of the application depends on the order or timing or sequence of the threads in order for it to function properly. So as you can see over here, this particular example we see here will not work properly if these are not ordered. And if they get ordered, if they get misordered, if the operations get interleaved, then you're going to have race conditions where you won't get the right results because your program is not properly protecting its shared state. There's another dimension to synchronization, which is coordination. And this goes by various other names. Cooperation is another term you often heard here in this case. I like coordination because that, to me, implies the problem to be solved, whereas cooperation sort of implies a way to solve the problem. So coordination is about trying to get things to occur in the right order at the right time. And it basically ensures the order of the threads run in is properly coordinated, so you get smooth handoffs and things occur in the right order. Now, some tasks, some concurrent programming applications have this property that we talked about last time about being embarrassingly parallel. So, single instruction, multiple data, go to town. There's no dependencies, there's no coordination necessary, and so on. So you can learn more about embarrassingly parallel computing here. That is not really an interesting problem, though. It's a great problem. If the problem you have is an embarrassingly parallel problem, the world is your oyster, because almost anything you do is going to work and scale quite nicely. More likely, however, in real life, you're going to have to find ways things coordinate with each other. You're going to have to make sure there are dependencies. Stuff plays at the right time. Stuff doesn't play. And maybe there's a master of ceremonies that keeps it all going, or maybe individual groups coordinate their own activities. So the interesting problems in concurrency are where you don't have embarrassingly parallel behavior. All right, so let's talk a bit about mutual exclusion. So the goal of mutual exclusion is to make sure that concurrent threads don't simultaneously execute in critical sections of a program. Now, you're going to see this kind of a diagram a little bit later as we get further into the discussion of Java concurrency and synchronization mechanisms. Does anybody know what this is a visualization of? It's a floor plan. It looks like a floor plan. Yes, it very much looks like the floor plan. In fact, that's not accidental. That's a visualization of a so-called monitor object. And as we get further into this stuff, you'll see that monitor objects basically behave a little bit like a room. And you get to learn more about this room metaphor later. And you have a door. And one thread at a time gets to come through the door. And as soon as the door opens, it shuts right away. It's like one of those things at the amusement park where you can only go through one at a time or whatever, or like airport security. And as soon as you're through, the door shuts. And there's only one thread here running at a time, and it's running. And this is a critical section. And when the thread is done, it will then go ahead and open another door and leave, which then can allow one of the other threads that's waiting to come in and run. And you'll see that there's some other cool stuff we'll talk about later that I won't go into right now. But that's basically the idea of mutual exclusion. One thing gets in the room at a time. Again, the restroom example is a good one. Maybe confession or something is another good one, right? There are lots of examples in everyday life where you need mutual exclusion. So one good example of a place you need mutual exclusion is an airport. In fact, we're going to see lots of airport metaphors here because it's a good example of a large, complex, mission-critical concurrent environment. And things like runways, you really only want to have one plane landing on the runway at a time. Now, if you have multiple runways, you can have things landing in parallel. It's kind of like a multi-core machine, right? But in a normal airport, one plane landing on a runway or taking off on a runway per time. So what you're basically doing is somebody, the air traffic controller, is synchronizing access to this shared resource to keep people from colliding. Good example of the importance of synchronization. A little bit more closely to home, we had talked about this before. If you recall, when we had talked about content providers, we'd mentioned how it's possible to have multiple threads of control in a content provider, like the contacts provider. And somebody, typically the SQLite database, has got to make sure to ensure mutual exclusion when accessing the contact information. So you don't want multiple threads sort of updating a contact and overwriting it and corrupting the database. That would be a really big problem. That's an example in Android. All right, so that's a really simple example. Let's take a look at, or that's a high-level overview. Let's take a look at an example. So we're going to come up with a very simple concurrent programming application where we're going to have two threads, a producer thread and a consumer thread. And you'll see producer-consumer problems are very, very canonical, very common in concurrent programming literature and textbooks. And what it's going to be doing is it's going to be putting, one thread is going to be putting stuff into the queue, and another thread is going to be taking stuff out of the queue. And we're going to call this thing a simple queue for reasons you'll see in a second. It should be probably called sort of simple-minded queue because it doesn't quite do what we want it to do. But its interface is based loosely on something called the array blocking queue, which is this cool feature that's a cool class that's provided in Java/Android that allows you to be able to do producer-consumer interactions between multiple threads using a buffer, which is the queue, and it blocks under certain situations. At the moment, we're just going to focus on mutual exclusion. We'll come back and cover some other parts later. So here's a UML.sequence diagram that illustrates the overall design and interactions in our producer-consumer example, which is Buggy. So we call it the Buggy queue. So it's going to start out by having a main program or a main method called, and that main method is going to go ahead and create a simple queue, and it's going to create a consumer thread, and it's going to create a producer thread. And then it's going to go ahead and start the producer and consumer thread. And as you'll see later, as we get into this in more detail, as you know, when you call start, the run method gets called back. And one of the threads, the producer thread, is going to go into a loop putting stuff into the simple queue. And the other thread, is the consumer thread, is going to go into a loop taking stuff out of the queue. So that's the idea. At least that's what we're trying to do, right? So here's our simple queue. And if you take a look here, you will find the implementation of what I'm going to give you the Cliff Notes version of. So here's simple queue. As you can see, simple queue implements blocking queue. A blocking queue is the interface that all the different kinds of blocking classes, whether it be a array blocking a list or array blocking queue, there's a bunch of different, or different kinds of things you can have. There are different ways of implementing this stuff. This is the interface you have to fill in. And our particular implementation, you can see blocking queue here if you want to read about blocking queue. Our particular implementation is going to use a resizable array implementation. So new array list. So it's an array list. It's an array that will be implemented as a list, and it can grow. So take a look, find the class here. Here are a couple of the methods that come out of the blocking queue interface, put and take. The intent of put is to add something to the queue, and the intent of take is to take something out of the queue. Notice how that these methods are not synchronized. And when you call put, the implementation here is going to add the message to the end of the list, and take is going to remove the message that's at the 0th location in the list. Okay, so far so good. Here's the main program. This is what does the work. It's going to start out by first it creates the simple queue, and then it goes ahead and it creates a couple of threads. This is the producer thread. This is the consumer thread. It then goes ahead and starts those threads. We'll look at this in a second to see what it's doing. As you can see, this does what we had talked about last class about anonymous inner classes. This is creating a new runnable whose run method will iterate and go ahead and put the iterator count as a string into the queue. So it'll go like 0, 1, 2, 3, 4, 5 up to max iterations. It'll stick the thing in the queue. And here's another thread which will sit here and pull things out of the queue. So those are the two operations. First of all, any questions about that? Is everybody reasonably comfortable? We'll talk about all this threading stuff in more detail shortly, but I just want to make sure people kind of get the overall idea. We're creating anonymous runnables that have run methods. We're putting them in threads, and we're starting the threads, and the run methods get called, and they do their thing. Any questions about that? Okay, so the question is, what will this program produce as output? What will the output of this program be? Let's make it easy. Let's say that max iterations is set to 5, just for lack of a better term. All right.
Well, if consumer somehow ends up running faster than producer, will an exception be thrown that says, my underflow error?
Great. So that's one thing we'll see. So one observation is there will undoubtedly be an exception if the consumer is running faster than the producer, because there won't be anything in the queue. And it'll try to read from an empty queue. Robbie?
Isn't that what the blocking queue prevents them?
It is, but if you go back and look, we actually didn't implement anything to make this blocking, right? That's why it's simple-minded queue, because it's too simple for its own good. So that's one thing. So what will happen is you're going to get scrambled output or an exception. So chances are, whatever happens, it's not going to be what you thought it was going to be. So bad things will occur. And then, of course, the question is why? And the reason is because there's no synchronization in here. There's no protection of these things. And so when the two threads run, they're just going to kind of run like crazy, and weird stuff's going to happen, and you're going to have race conditions galore. Okay, so that's one class of problem. And oh, by the way, if you were to go and look at the array list documentation, you would say that this implementation, you would see it says this implementation is not synchronized if multiple threads access an array list concurrently and at least one of the threads modifies the list, like we're doing here. We're adding and removing stuff. It must be synchronized. In other words, there must be an external lock, synchronized block, synchronized statement, reentrant lock, whatever, to make sure that the state does not get corrupted. Okay, now, as it turns out, if you were to run this program and you didn't know what we're about to talk about, you would probably be somewhat befuddled. And that's because, of course, synchronization is an inherently complex issue. And therefore, when you start trying to program systems that require synchronization and you do it wrong, it's really frustrating because things are going in the wrong order and you're ending up with data being corrupted in all kinds of crazy ways. And as I mentioned last time, if you have a multiprocessor or a multi-core system, you'll probably have these problems reveal themselves much more quickly. But if you don't, half the time it won't show up. And therefore, you'll be perplexed when your users or your customers or your graders say, hey, your program doesn't work right. And you're like, but it worked for me. And they happen to be running it in a different context. So these are really tricky things. We're going to fix these problems later. And we're going to use, of course, the monitor object mechanisms. We're going to make a synchronized queue that is much cooler and easier to work with. OK, so that was basically mutual exclusion. Things are going to get corrupted because we're not protecting the state. Let's talk now about coordination. So we talked before about coordination ensures things occur in the right order at the right time. So it's related to mutual exclusion, but it's sort of a different dimension. And in some sense, it's a more interesting dimension. Mutual exclusion just says one thing at a time. But coordination has a lot more subtlety to it because things can occur in all kinds of different orders. And sometimes those orders matter and sometimes orders don't matter. Once again, if you think about an air traffic management system, you can imagine having a situation where you want to coordinate the various resources in an airport, right? What do you have to coordinate in an airport? You have to coordinate arrivals of airplanes to gates. I don't know if you guys fly very much. I fly a lot. And one of the most annoying things when I fly is to get to the airport half an hour early because of a tailwind, and you land, and then you're sitting there, and you're like, well, there's a plane parked in our gate, and we can't let you off, right? So you get there early, but you can't really leverage this in any useful way. And that's because these things are scheduled, right? And so things have to occur in the right order. And if they don't occur in the right order, all kinds of inconveniences or maybe even potential hazards occur. So being able to schedule access to shared resources so things happen in the right order is very important. This kind of stuff also applies in your phone. You might be playing Angry Birds on your Android phone or your iPhone, and all of a sudden, an emergency call comes in. And the system has to make sure that it knows how to preempt your Angry Birds game because the emergency call is probably more important than playing Angry Birds. So it's got to keep track of all the things that are running, and it has to know how to stop some things and start some things. And sometimes you want to stop things voluntarily. You say, well, take your time. When you're done, then go ahead and pause yourself. Other times you want to preempt something. So there's a bunch of other subtle issues there. What makes this hard in concurrent programs, and you guys are going to discover this when you start trying to debug your fair implementation for the current assignment, is there's a lot of states your system can be in. And you have to basically learn to think through all those different states. At the very least, what you're going to have to do for this assignment, you're going to have to think through, sort of a couple of different threads, which one is acquiring the lock, which one is releasing the lock, what's the order that they're going in, are you properly protecting that internal state, like the count, the permit count, are you ensuring you're going to wake up an appropriate thread when you release the semaphore, you're going to wake somebody up, right? Those are subtle things, and you've got to sit there and think through all those different states that are potentially going to happen in your program. And that takes a while. It takes your head a while to get used to thinking concurrently, especially if you're not really using the right set of tools. So let's take a look at an example that kind of illustrates how all this stuff works. This is an example that has two Java threads that are going to attempt to alternate printing ping and pong to the computer console. So one thread's going to print ping, and the other thread's going to print pong. Or that's what we want to have happen, right? So it's an alternating protocol. Well, what's going to happen here when we do it with this implementation, this is the ping-pong wrong program, is that ping-pong wrong is not going to give you the right order. Instead, what it's going to do is it's going to run all the pings first, followed by all the pongs. So that's clearly not properly alternating pinging and ponging. And you'll see that there's a bunch of subtleties here. And of course, in Android, it gets even more complicated. And you'll get a chance to play around with this later, because we'll have this as one of the assignments. All right, so here's a diagram showing the design of the Buggy program. And then we'll come back later and we'll show you how to fix it to do the right set of things. So there's the main thread, which is the entry point into the ping-pong wrong program. It goes ahead and creates a ping thread and the pong thread, and it starts them. And then they're going to go ahead and print ping and pong. And when both threads are done, it's going to go ahead and the main thread will wait for the other threads to finish. So the run call gets called, and you can download the ping-pong wrong code here just to play around with it as well. All right, so let's take a look at the code, and maybe you guys can think as we're walking through the code what's wrong with it and how would you fix it, because it's kind of an interesting exercise to try to do this. So here's ping-pong wrong. We have the number of iterations to play. We'll play 10 iterations unless we go ahead and change this. Here's the play ping-pong thread, which is a thread. So we extend thread, and we're going to use this to actually drive the main computation. We then go ahead and keep track of the string we want to print, which will either be ping or pong. That gets set in the constructor, as you can see here. And here's the run hook method. When this thread gets started, it's going to go ahead and run this method. You can see it goes into a loop. It loops for 1 to max iterations. Every time through the loop, it's going to go ahead and print the string to print, which would be, ping. And then it's going to print the loop count inside parens. So as you can see back here, that ends up resulting in this, ping or pong. Now, it literally is doing that because it's wrong, but we'll come to that in a second. OK, so that's pretty much all the program does. Notice that there's no synchronization here, though. So as a result, there's nothing to prevent the threads from printing in random order or interleaving in a random way, or the first thread runs to completion, then the second thread runs. So all kinds of bad things can happen. And later we'll come back and fix this problem. And then when the run method is done, that will leave the method and the thread will be finished. It'll terminate, basically. We'll talk about that more later, too. Here's the main entry point into this program. We go ahead and create a new play ping pong thread with the word ping in it, and another play ping pong thread with the word pong in it. We go ahead and start those two threads, and then we go ahead and join ping and pong. Does anybody know what join does? Hopefully it's clear from the example. What would you think join would do? Well, let me rephrase that. If we didn't put a join here, what would happen? What would happen would be we'd start those two threads, and then the main thread would just exit. Which, by the way, isn't the end of the world. That's not really a problem in this case. In this particular case, we wanted to make sure that everything was done before we printed done. Right? That's the only reason we did this. We wanted to synchronize on the completion of those two threads that we started. So join is basically a synchronizer, which waits for the thread to complete, and then it will go ahead and continue. So join blocks until the thread it's called on is finished. What does it mean? How is a thread finished? What happens? How do you know when a thread is finished? Its run method is no longer running. We'll come upon this later, but there are two basic ways that run can stop executing. Does anybody know what they are? Finishes or throws an exception, exactly. So the normal case is it just falls off the bottom, right? You get to the end of run. The other cases where an exception is thrown that is not caught or handled by the thread, which then causes the thread to exit. OK, so that's basically what the program does. So what's interesting about this is basically we have this program, and it's got, we create new threads, we start them, they run, we join them, blah, blah, blah. Everything looks good. All the things that are important about threads are shown in an example. Oh, but there's one big problem. It doesn't work properly. And as we saw here, the reason it doesn't work is because there's no synchronization. So in one ordering, all the ping stuff goes first, followed by all the pong stuff. You can imagine if we ran this for a longer amount of time, you would probably see an interleaving of ping and pong, but it wouldn't be alternating. What we want is it to look like this. We want ping, pong, ping, pong, ping, pong for each iteration. And the way we're going to do that, and the way you're going to do it, is we're going to use Java synchronization mechanisms. In your particular case, we're going to implement a binary semaphore, which should be really easy after you implement a counting semaphore, because a binary semaphore is kind of a lobotomized counting semaphore. And then we're going to use that to implement the program. We'll play around with some other stuff. You can also use other things. You can use a semaphore. You can use condition objects. There's all kinds of stuff you could do in order to properly synchronize this program.